Okay, let's get started. First, let's quickly recall what we did last time. Starting from section or lecture note 2, we start talking about rigid body configuration and velocity. This should be something you have learned before in a way that maybe in this way, but maybe in the more like a DH or other type of elementary approach. And we'll start to kind of tell you should think about coordinate-free way about rigid body configurations. I think I encourage everyone. Some of you may think that's trivial, but some may not. I will encourage everyone to go over this proof. This will be super simple proof about RBA, right? Given a same vector in B and A, their change of coordinate of that free vector is RBA times VB. It's give you the coordinate of V in A. So this is a super simple proof, but just get you started on this kind of a coordinate-free thinking and what does that mean if you choose a coordinate to express the physics. Okay, you will see a lot more about things like that. This is the basic elementary starting point. Okay, we start introducing rotation matrix, and rotation matrix by definition is trying to represent the pose or orientation of one frame with respect to others, right? If I write like this, if I write like this, what does this RBA means?
It means check the coordinate of vector V
from B to A.
In B frame to A frame.
Okay. Well, that's correct. But what I want you to answer is still RBA is the orientation of B in A. Okay. Definition never changes unless we start from a different way to define it. The way we define RBA is always the orientation of frame B in A. It's just this formula, right? We don't change it. But this is a property that we conclude the definition we just introduced has this kind of formula, right? To relate vectors in B to A. You have to separate definition from properties. Okay, you cannot have too many things, because last week I asked many of you about what rotation matrix is, and most of you think about rotating something. That's a very advanced way of defining a rotation matrix. We will see that in lecture 3. But for now, let's think about RBA is just orientation, okay? And it has a property. Because we define this way, it has a property that to change coordinate, and we derive why this property holds. Okay, then we start to here. I think we stop here, right? So orientation does not fully specify things in the space, and if we want to truly kind of characterize geometric relation between two frames, we have to know the origin. Okay, not only the orientation. Let's say we have two frames. One is A, the other one is B, okay? Their origins are not co-located. They are located at different locations in the space. Now I'm going to ask questions, all right? What is RBA here? Come in. What is RBA here? I say RBA now. RBA. A, right? Definition don't change. Okay? Otherwise, you need to remember too many things. There's just one thing. What is, let's say, what is XB? A. This may be XB hat, YB hat, and ZB hat. It's, but then I'm going to ask you too many things, all right? Is this XBA the same as XB hat here? Is this the same as this? It is, well, it's the coordinate of this vector in frame A, okay? It has few numbers, but you're trying to represent this vector in frame A. That will be its coordinate, okay? Let's do that. Now I'm going to ask you another question, maybe not Fujin. OBA, what is OBA? This is OB, this point is OB. How do you represent a point? Using vector. A point is a point. You need another starting point to define a vector. Where is the starting point? OA. Why? Because we choose A frame to represent B, right? So this will be this vector. Okay? And this vector, and you represent this vector. So this vector is a physical quantity, all right? This vector, I want to represent it in A, then I will have a coordinate in A. I can also represent this vector in B. That sounds a little bit weird, but it's fine, right? It will have a different coordinate. So OBA is just this vector. This is called OB. Let's call OA, OB this vector, right? I need to represent it in A frame. Okay, that's a little bit about review and a little bit about emphasis of disconnect coordinates or numbers from the actual physical meaning. All right. Now I'm going to ask another question. Suppose I give you a free vector, okay, a vector R. Let's randomly draw a vector. This is R. This vector is uniquely defined. Vector only involves direction and magnitude. Okay, so now I'm going to ask you what is RA. Let's say how RA relate to RB. Now I'm considering, right? I'm considering two frames, and the frames are not collocated. Stefan, what's the relation between RA and RB?
That's the big R, RB, A times little R
equals to RA, but they are not at same location.
So in this case, the rotation matrix or the orientation transport that little RB.
Okay, you think that's true, Xinhan, right? No? You think it's no? Why?
You need to.
Let me tell the answer. This is correct. Although Daifeng may not know it's correct. And why it's correct? By definition. What is a vector? How do you represent vector in frame? You move the vector to the origin to that frame and use that frame to represent that vector, right? And you move, if I want to represent this R, then I need to move this one to here. And if I represent the A in B, then I need to move that to the origin of B, and then use the coordinate system to represent that vector, right? It's not a point, it's a vector, okay? It doesn't matter how far these two frames are. Only the orientation matters for a free vector change of coordinate, okay? I hope you can start thinking more precisely in terms of definitions, in terms of coordinate free of thinking. Okay, that's gradually being trained throughout this semester. Okay, now a different question. Okay, now I have a point. Point is different from vector. Before we think, well, even before I read those books or learn those stuff, I think they're the same. But now you have to separate point from vector because physically they are different, okay? If I give you a point, let's say this is my P, this is the point. Now I have two frames. Okay, one is frame A. This is a A frame. This is my O of A. I will have another frame B. They have different orientation and different. The central origin is also located at different location in space. So now I'm going to ask you, what is the coordinate relation between PA and PB? What's the relation? How do you think? Daifeng, do you know this relation? Is RBA times PB? You learned this, right, before? Maybe through formulas or what?
Yes.
Still same? Okay. Okay, I see. Yinghan, this time's different. This time you are wrong, he's right, okay? Okay. If you don't know, always start from definition. What is P of A? So we have a physics right here. This should be my vector to represent P in frame A. This I call OAP, this vector, right? And this is my vector. If I want to represent P in frame B, then I have a different vector, right? This is my OBP vector, okay? I also have another vector which is relates this origin. Let's call it OA, OB thing. Okay, coordinate free, I didn't say which coordinate yet. Okay, there's three vectors physically there, regardless of what frame we use. So let's think about coordinate free. I'm going to emphasize that again, coordinate free of thinking. What we can conclude is the following: is OAP vector equals to OAOB plus OBP. Do you agree? Right? If you, but vector can be moved around, okay? Once you define the vector, it's not point. Okay? Vector can be moved around. If you do that, that's exactly the physics, okay? But we can choose different coordinate to express this physical law. I wouldn't call it law, but anyway, this is a fact. All right, so let's choose, say, let's choose A frame to represent, to let's call to express I'm abused the term physics a little bit, so I don't think it's physics anyway. Or the simple geometric fact. What we got is OAP in A, right? Equal to OAOB PA in A plus OBP, this vector in A coordinate. Okay? Now you should be able to see what is this. This is my PA, right? PA vector is OA point to P expressed in A frame. And OBP, this guy is this, right? Sorry, no. Is this? What is this? OBP. So this guy is this vector, right? This vector. I know this vector in, I can say P in B will be this vector in B, but I want to express that in A, right? So this will be, this guy will equal to PB times RBA, right? So this one is, this is A, right? This guy is OB, the point of the origin of B frame in A, right? So overall we have This guy is OBA plus RBA, that. Is the origin plus the point in B, then change the coordinate to A. Is orientation plus this displacement. Okay, but that's this whole thing is a little bit high school geometry. You choose a coordinate, you can do that. All right. Any questions so far? Definitely makes sense now? Yeah. Okay, good. These two are different. All right. Now let's do a little bit more. Okay, we have seen that the relation about the point, let's say PA equal to, let's say, OBA plus RBA times P of B. Okay, we derive why this is the case. You should be able to derive everything that you see, okay? Before you may just memorize this, but now you need to know exactly what's going on. Okay. This is not more precisely speaking, this is not really a linear relation. If we see this variable, this is a variable vector in R3, these two are related by a matrix times this plus vector. Okay, this one is R3, right? This guy in R3, this is 3 by 3 matrix. Okay, so these two PB and PA are related by a so-called, this is a fine, a fine relation. Okay, this is a linear relation. But in general, sometimes we also call fine a linear relation sometimes, but more precisely, this is a fine. Okay, it's just the relation doesn't really precisely pass through the origin. You have some offset vector OBA. Okay, we can make it a pure homogeneous linear function by lifting this PA. Let's see, equal to, let's define it PA1. We can check later. Okay, RBA. This is OBA times PB1, okay? Here is 0, here's 1. The second row doesn't have much information, 1 equal to 1, right? The first row just express this expression. It's RBA times PB plus OBA, and this guy is a 3 by 3 matrix 0, okay? This guy is R3, right? This is 1 by 1. So overall, we have a 4 by 4 matrix. We can define this matrix, which we call homogeneous transformation matrix, TBA, equals to RBA, OBA, 0, and 1. Okay. It's just putting together everything you need to change coordinate or to represent frame B in A. Okay. So orientation, let's recall. Okay, orientation of B with respect to A is completely characterized by RBA. That's orientation, right? To really know the spatial relation, you need to know OB as well. So you need to know these two things, right? These two things defines all the relation between these two coordinate systems. And a good way to organize the information you need is to construct a so-called homogeneous transformation matrix. So T, in general, in short, we can write like TRP. Okay, that's a notation that means whatever it is, a homogeneous transformation matrix. We call this the configuration of B relative to A. Configuration need orientation and also the displacement of frame B origin with respect to the frame A origin. Okay. So if we want to use that, then everything starts to look like orientation, because let's see, we can say given a point, we call it P in R3, it's homogeneous. It's called homogeneous. It's homogeneous coordinate. Is given by P tilde equal to, let's say, P1, which is in R4 now. Okay, we just add one constant element to the bottom of P, make it a 4x1 vector. And if we do that, we know that P tilde A equal to TBA times P tilde B, okay? It becomes linear. So this is a linear or homogeneous, okay? This is a affine relation. Okay, that's, now I'm gonna ask you another thing. Let's say given a vector, V, it's homogeneous coordinate. Stefan, what do you think? It's called V tilde.
It's column vector
V
is V and the next one is Y.
Okay, that's the coordinate. That's wrong. Okay. No, the coordinate, homogeneous coordinate. Well, intuitively you want to do this. Okay, but V is a free vector because it's typically V is, for example, you can think about V as a vector, right? From one point to the other point, and you can move it. So V tilde is P1 tilde minus P2 tilde. So this one is 0. Okay. For free vector, it's homogeneous coordinate. Maybe we don't use that much. Okay. It's homogeneous coordinate is V, and the next one is 0. That's free vector. Okay. Point, you need to add 1. Right. That's a little bit counterintuitive, but that's some important fact. Maybe later on you will see a few places. This will help you to understand the result. Okay. So no matter it's vector or what, the homogeneous coordinate transformation can be always written like this. Okay. Right. Let's check. Let's just further explain this a little bit. For example, we, Devon, you were right about this, right? Okay, let's do homogeneous transformation for this. Homogeneous extension. If I say R tilde A, it's RA1. Let's say that, okay? It's wrong. And RB tilde is RB1. then I cannot say BA or B tutor anymore, right? You see what I mean? Because the first row would be, this would implies RA tutor equal to what? OBA plus that. You have a one term. So if I write like this, okay, then R tutor A, if you multiply the first row out, I'm not sure, I don't want to write everything out, will be OBA plus RBA, R tutor B. You see what I mean? Okay, because there's one here, the origin effect somehow kick in. So this is wrong. Of course, this is wrong, right? This is incorrect. Okay, so in general, I have too many colors. So R tutor A, by definition, this should be 0. Okay. Any questions? This is about homogeneous coordinate. We spent maybe 10 minutes for this, and then that's about almost all you need to know. Let's have an example. This example almost like a trivial or toy example. Let's think about we have a robotic arm, and there's a camera mounted on at the end of the end effector. Here is the camera. This is my workspace. This is a table. This is a B. B is what? End effector. B is end effector. Oh, this is a camera. Okay, this guy is the camera. And workpiece frame is D. And this is A is almost a fixed frame in the space. And suppose PC minus PB, the distance between these 2 points, this is 4. Okay. Now I have all the geometry information you need to know for this robotic station. And my question is, let's say, what is the camera location? Of course, when you ask the location, you always refer to certain frame, right? You need to fix the frame. Let's express it in the fixed frame. How to represent it? Homogeneous transformation matrix. That's basically, in other words, is like you need to know. That's called C camera. Right? You need to know RCA and OCA. Right? You need to know these 2 things. Okay, but typically we write it in the homogeneous transformation matrix format. You need to know or specify this is, if I write it like this, no matter how I write it, you think about this as a 4x4 matrix of that special form. Okay, RCA equal to 0, 1, 0, 1, 0, 0, 0, 0, -1. Well, I can directly write it. I'm not sure whether you feel okay. RC is the orientation of C frame. Let me start over again, okay? Let's say RCA. So then, how do you write it down? RCA. What's the first column?
First column is 0, 1.
No, not tell me the answer yet, okay? RCA, first one is XC in A. Where is XC? This guy is XC, right? XC is a free vector. XC is not a point. You see, I can move this XC to A frame and find its coordinate. That will be my XC in A. So XC is pointing to this direction. It seems like it coincides with YB. Okay, so XC in A would be, I can directly write it down 0, 1, 0. Right? Yangxing, what does this 0, 1, 0 mean physically? Coordinate. Right? That means this 1, 0, 1, simply stating the following fact. XC is 0 times XA hat plus YA hat, 1 times Y hat plus 0 times ZA hat. This number means physics or geometry, right? This just means that. It's a shorthand notation, but we have to agree upon this. Yinghao, that makes sense? Okay, that's exactly saying this. And this equation does not have any coordinate. It's just all the physical vector relation. Okay, I think that's good enough for us to move on. And the second column is YC in A. YC coincide with XA, which will be what? 1, 0, 0, right? And ZC is the negative of ZA, so it's 0, 0, negative 1. Okay, it's quite straightforward if you know what's going on. And what about PC? Sorry, I call it PCA now. Did I use P anywhere? PC and PB. Okay, let's call it PC. Sorry, point. This is sometime I change this notation. P, and the PC in A, what is it? Therefore, you should PC in A. Which vector? This vector, right? This vector. You can think of that projected into this plane, and what do you think his number is? -1. Yeah, here is 1, right? So -1, 1, and 2. I hope you get it, right? So then my homogeneous transformation matrix will be just R, PCA, RCA. This is 0, 0, 0, 0, 0, 0, 0, 0, 0, and oh, sorry, no. I think I made some mistakes. This is what? 0, 0, 0, this is 1. Okay, if I write everything out. 4 by 4. I think I say something wrong before. 3 by 3. This is 1 by 3. Okay? This guy is 1 by 3. All right. Then some people may ask, typically you need to compute the end-effector frame location, maybe. Then that will be TCB, TBC. Oh, sorry, TBA, right? I want to know end-effector frame TBA. Now I'm going to tell you a fact that you can derive at home. So let's say TBA would equal to TCA times TBC, right? By notation wise, it looks intuitive, but I encourage you to prove it or think through why it's the case using you have learned so far, okay? Can you? I think so. Okay. If that's the case, well, we know TCA, right? We know TCA, so we just need to compute TBC. I think that's easy to construct, TBC. I can directly write it down. TB in C, let's say TB, the first column, the rotation matrix part, is the same, right? Oh, they are the same orientation, are they? Yes, so this is 1, 0, 0, 0, 1, 0, 0, 0, 1. And what about the PB in C? Will be the x coordinate is -4. The others are the same. So that's 0, 0, 0, 1. That's my matrix. Okay, and these two multiplied together give you TBA. And you can also find TBA directly by definition, but I'm just telling you, you can do it this way as well. Maybe this is the homework for you. Just ask you to think something you typically don't think. You will find out that once you understand the basics, the advanced stuff is not that hard. Okay, the foundations are so important. Otherwise, you need to memorize everything. Okay, so you need to summarize some kind of not science, so some kind of rules, but understand the foundations are very important. If no questions, let's move on to the next very important topics.